on, we're looking at question number 11 of winter 18, paper 419702. The question reads, a stationary isolated nucleus emits a gamma ray photon of energy 0.51 megaevolt. State what is meant by a photon, and it's for 2 marks. If I were to describe photon in simple terms, so whenever you have like an electromagnetic radiation or you have light, the smallest of the smallest particle of these things is a photon. So if I were to write it in an answer, I would say it is the quantum of energy. So it's like electromagnetic radiation, electromagnetic energy, or any form of energy, and the smallest particle of that is a photon. So I can say it is defined as quantum. Quantum is like a packet of energy, is quantum of energy of electromagnetic radiation. And then you have the B part that says, for the gamma ray photon, we're going to talk about the photon, and that is, we have to find out its wavelength. Now that we are dealing with photon, you should know that there is some energy, because we just said that it is the quantum of energy. That means a photon contains some amount of energy, and that energy can be E equals h f, where h is the Planck constant, and then you have our frequency. But we have to find out wavelength. We do know that v equals f lambda, something that we learned in waves chapter, v is equals to f lambda. I can have v, and in quantum physics we denote v with c, which is 3 into 10 raised to the power 8, a constant, and then you have c over lambda equals frequency. So our final formula becomes energy equals hc over lambda. Now there's one more important thing that we need to discuss. We know they have given us the energy. Let me write this here. They have given us the energy 0.51 megaevolts. We have the Planck constant, we have the c, we have to find the lambda. The mistake that most students make is that they just write 0.51 as it is. One set thing that you always need to ensure, every time you use energy in questions in quantum physics, you must ensure that energy is in joules. That is, I feel like, an extremely important point, which if does not happen, that can mess up our question. So we know that 0.51 megaevolts, we need to convert it into joules to be able to use it in this question. How do I convert megaevolts to joules? It's better if you learn this conversion, because this conversion isn't given at the beginning of your paper, so you should learn it ideally. That says 1 megaevolts equals 1.602 into 10 raised to the power minus 13. And now that we have our energy, we have this conversion, you can multiply 0.51 with this. We will write h, which is 6.63 into 10 raised to the power minus 34. 6.63 into 10 raised to the power minus 34 into 3 into 10 raised to the power 8, which is our C here, and then let me move it here. We divide this by our energy, which is 0.51 into 1.602 into 10 raised to the power minus 13. Into 1.602 into 10 raised to the power minus 13. So we have H 6.63 into 10 raised to the power minus 34. Then we have our F. Then we have our C, that is 3 into 10 raised to the power 8, divided by energy, which is 0.51 into this multiplied by this, because we have to write it in joules, and the wavelength that you get is 2.4 into 10 raised to the power minus 12. 2.4 into 10 raised to the power minus 12. Moving on, we have the momentum. It's momentum. Now, when you're dealing with momentum, when you're talking about the momentum of a photon, we use momentum equals energy over C. But if you're dealing with the de Broglie's wavelength, where you're saying that they have wave-like properties, that is when you use lambda equals h over momentum, where h is the Planck constant, then you have the wavelength, and then you have the momentum. But here we're dealing with photon, so we will be using this formula. Again, we have all our values that we need, pretty straightforward. We have momentum that we have to find, energy was 0.51, and then you have to multiply it with 1.602 to the power minus 13, 1.602 into 10 raised to the power minus 13 over speed, which is 3 into 10 raised to the power 8. 3 into 10 raised to the power 8. And when you put this in calculator, the answer you should be getting is 2.7 into 10 raised to the power 2.7 into 10 raised to the power minus 22. Okay. Moving on towards our C part. For this nucleus, so we had a photon. So initially we have a nucleus that emits a gamma ray photon. Okay, so we have a decay happening. Determine the change in mass during the decay that gives rise to the energy. Now, every time you see these two words together, mass, energy, that there has been a conversion of mass energy, that there was some energy that was converted into mass, or mass converted into energy. One formula that should instantly pop up in your mind is the Einstein equation, which is E equals mc squared, the legendary equation. What this means is that whenever you have a decay, since everything is conserved, so energy, mass is conserved, which is to say that energy can be converted into mass, mass can be converted into energy, but it's going to remain constant. There's just going to be an interchanging that can happen, like they have said here, that the change in mass during the decay that means there was some change in mass that was that gave rise to this energy. So again, this is the change in mass, this is the energy. We have the energy, we have our c square as well. We have to find the mass. E is again 0.51 into 10 raised to the power into 1.602 to 10 to the power minus 13. and it's so important to convert energy into joules, because you can see how in all of the parts that we did before, energy was needed, and if you had just written 0.51, that would have cost you all of your marks. And then you have the mass, which we have to find, and then you have the c square, which is simply 3 into 10 raised to the power 8, and then you square it, and you should get the mass like this. The mass that you should be getting is 9.1 into 10 raised to the power minus 31. Done. And now comes the second part that says explain why after the decay the nucleus is no longer stationary. If you look at here, we found its momentum, and we do know, let's try to visualize this. Let's assume that I have my nucleus here, and it just gave off some like gamma ray photon, and that photon traveled in this direction. But if this keeps traveling in this direction, I have to make sure that momentum is conserved. So I have to make sure that this moves in opposite direction to ensure that no new momentum is invented and that momentum remains conserved. So I can say that momentum is conserved, so nucleus must have momentum in opposite direction to photon. Since the momentum remains conserved, the nucleus must have momentum in opposite direction to photon. And this is it for the second part as well, and for question number 11.